Hello, Integrated Science. This is Mr. B, and we are moving on with Section 2 of Exploring the Universe, and this section is about stars. So Section 1 was about the Sun, which in itself is a star, but now we're going to talk about more stars in general and kind of stars outside of our own solar system that might be present throughout the rest of the universe. So to start here, to give an example, there's a star Proxima Centauri, this big red star. I just tried to point at that with my finger. You guys can't see that. The Proxima Centauri, the red star in the center, this is the closest star to the sun. Then we're going to start figuring out how do we figure out how far all of these stars are away from us. So a star is a large glowing ball of gas in space which generates energy through nuclear fusion in its core, which sounds very similar to the sun, which again, our sun is in fact a star. The closest star to Earth is the sun, which is considered to be kind of a fairly average star. So we're going to get going. We're going to talk about how they classify stars based off of kind of their size, the amount of energy that they produce. So the sun, pretty middle of the road, average star there. So the first thing that we're going to talk about in this section is going to have to kind of be some tough to explain necessarily all of the video, so we'll have to do some in class as well, is how the distance to a star can be measured. And we do this using a method called parallax. So the apparent change in position of an object with respect to a distant background is called parallax. And again, we're going to explain that more as we go because that might not make a ton of sense now. So astronomers measure the parallax of nearby stars to determine their distance from Earth. So again, we're going to talk about that here in a little bit here, about how a parallax works, but we're going to get a couple other definitions and kind of explanations leading up to that first. Because stars are in fact so far apart, it's not practical to measure their distance in units that might be used on Earth, such as kilometers. Again, our numbers would be too gigantic, they would be too hard to work with. So instead of using measurements that we'd use on Earth to measure objects in space, we have what's called a light year. And a light year is the distance that light travels in a vacuum in a year. So again, you've heard people say, well, you move at the speed of light. That means you move really fast. So light actually you can measure how far light would move in a year. And in a year, again, light would travel in a vacuum, and that means like uninterrupted by anything. So when something happens in a vacuum, it means completely by itself. There's no outside forces bending the light or stopping the light. Because again, you shine a flashlight against the wall stops the light. So a vacuum would just be if light could just travel forever without anything getting in its way, it would move 9.5 trillion kilometers in a single year. So it's very long distance again. Uh, and so again, it would be very impractical to just write out 9.5 trillion just for one light year. So that's why we kind of have it broken down there. It's because Proxima Centauri, which is the closest star to the sun, is about 4.3 light years away. Again, closer to 40 some odd trillion kilometers away from where we're at. Again, so those numbers would just get too large to work with, so that's why we kind of have it broken down to a light year there. And then stars, so here's getting into how the parallax works. Stars are so far away that astronomers cannot measure their distances directly. Instead, we observe stars from two different positions on opposite sides of Earth's orbit, and we can notice that as they orbit and as they move, they are moving against the more distant background stars. So there are stars that are closer that, again, if you study them, which we can't see them moving just in one night, but if you study them over the course of, let's say, 6 months, you will notice that one star has apparently moved in the sky. And the reason why it looks like it's moving, it's based off of Earth's orbit and things like that. So you can observe parallax by holding your thumb in front of you and looking at it first with one eye and then with the other. Again, we can kind of talk about that in class. But how it works in measuring stars is we measure what it looks like from Earth in January. We can measure the star. Then we measure what the star looks like from Earth in July. So we have to go 6 months apart. And then there's a bunch of geometry that goes into this, which I tried to do a little research on it, and again, it has to do with measuring the tangents and angles and things like that. But basically, we have a triangle forming right here, and again, you can use simple geometry based off of these distance in this triangle, the distance in this point, distance to that point, kind of the angular changes. Again, a lot of that has to do with angles, which again, I'm not going to pretend to be an expert on this, but By having these two different measuring points and seeing how far the star has apparently traveled, again this nearby star compared to these distant stars, we can get an estimate about how far away those stars actually are. So like I said, it's a much more complex process than I can probably can explain to you, but that's kind of my best thing. We measure the distance from two different points. Again, using some geometry based off the angular changes that are made, we can estimate the distance on how far that star is from Earth. With the invention of the telescope, again, we could measure these positions much more accurately. Again, the closer star to Earth, the greater is its parallax. Again, that just doesn't really sound like it makes sense, but again, the greater the parallax, the closer it is to Earth. Again, astronomers have measured the parallax of many nearby stars and determined their distances from Earth. And again, that's not something that you can just do from one day to the next. It's going to have to be like almost 6 months apart to gather that information. Again, with present technology, the parallax method gives reasonably accurate distance measurements for stars within a few hundred light years, which again, few hundred light years could be as many as 450 trillion kilometers, somewhere around in there. But again, that's just, again, in this time of space, it's not really that big. Astronomers have developed other ways to estimate distances to more distant stars, but the parallax method is still kind of the best. And again, we'll discuss that more in class, help it make a little bit more sense. But that's it for this video. Let me know if you have any questions.